Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows. So I am being the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pan. In this class I am trying to discuss about the topic and trying to solve questions based on that, which may help you to solve your weekly assignments and the upcoming examinations. So let's start. So in the last week last 2 weeks I was discussing about the oxidation. So it's almost so there are 3 types of oxidation we have told. First is aldehyde oxidation. First is alcohol oxidation. If we take a primary alcohol, it will give a aldehyde after oxidation. If we take a secondary, it will give a ketone, and if we take a tertiary, there will be no such oxidation. Whereas if we take a strong oxidizing agent, it will lead to an acid instead of aldehyde because of 2-step oxidation, where it's going to aldehyde, a further oxidation leading it to acid. We have also discussed about double bond oxidation. There are 3 types of double bond oxidation we have discussed. If we have like this, there are 3 types of double bond oxidation. First one is the dihydroxylation. Second is epoxidation. And third is ozonolysis. All these 3 I have discussed in the last classes. So there is one question. It is one of the previous year question. So they have given this compound and performed and added O3, acid and H2O. Whenever we are adding O3, that means it's a ozonolysis. Now they have added H+. In the last class, if you have missed this class, you can go and check. In that class I have said that if you are adding zinc along with zinc or Me2S along with ozone to quench the reaction, then the reaction will be quenched at the single oxidation step. That is after this cleavage, it will just stop at this step. But if when you use zinc ozone with zinc or Me2S, in that case reaction stops here. But if we add any oxidizing agent like H+, or if we add water, what happens? The reaction get further oxidized, as oxygen is already there in the mean medium, and it forms acid. We have discussed about all these things. So now what will happen in this case? Here from the options you can see there is no such acid formation, so you have to consider that they have also added zinc here. Okay, from the options also we have to get something that they haven't showed any acid formation, I think. Okay, they haven't showed any acid formation, so you have to consider there is a zinc has been added into it. So they asked what will be the X acetone will be there and 2 molecule of formaldehyde will be there, then what will be X? Now I have showed you the shortcut to get this ozonolysis reaction. What was that? If we just cleave along this double bond, if we just cleave along these double bonds, two molecules of formaldehyde and one molecule of acetone. If you just cleave these double bonds, what will happen? We are just cleaving the double bond and I will add one oxygen to each part. So after cleaving, it will be, there will be oxygen and this part will be eliminated, so there will be an oxygen. Okay, similarly this part will be also cleaved, so there will be an oxygen and there will be oxygen also. So these two are formaldehyde, these two are formaldehyde, these two are formaldehyde. So two molecules of formaldehyde, this is acetone, so one molecule of acetone, so the product will be this one. So let's see which one is matching with this one, this. So correct option will be option B. Okay, this is the shortcut. You don't have to go into the mechanisms and all. You just, if you want to get the product of the reaction by ozonolysis, just split the double bonds and add one oxygen to each part. Add one oxygen to each part. Okay, let's go to the next one. So I have talked about this one. Yes, in the last class we talked about the epoxidation reaction. So I gave a homework from that what we will do if you want to do the epoxidation in a stereoselective manner. Now if you are given a double bond, you are forming the cyclopropane ring, that epoxide ring on it. Now the thing is, suppose you have given a double bond. Double bonds are planar because of the sp2 hybridized. Double bonds are planar. Now if you have given a double bond, now the question is, from which place the epoxide will form? The epoxide will form from the above the plane, or epoxide will form from the below the plane. You're getting it right? If you think your double bond is in the plane, your double bond is already in the plane because of the sp2 hybridized, because these two carbon are sp2 hybridized, and sp2 hybridization means planar. So this double bond, both the carbons are sp2 hybridized. So this is totally planar. Now the question is, epoxide will form just above the plane or below the plane. So if you want to control the epoxidation of the double bond, the stereochemistry of the epoxidation, so to get that kind of problem, Sharpless came out with this strategy where Sharpless epoxidation reaction is an enantioselective chemical reaction to prepare 2,3 epoxy alcohol from primary and secondary allyl alcohol. So by this process we can form selectively by changing the nature of the reagent, just changing the nature of the reagent, we can control the stereoselectivity of the reaction. So instead of MCPBA, here we have to use tertiary butyl peroxide. This one, just MCPBA is this, metachloroparbenzoic acid. So MCPB is this is MCPB. Okay, this is hydrogen peroxide. So you can see the similarity of the structure. This is also a peroxide. This is also a peroxide, tertiary butyl peroxide. Instead of this big group, we are using this tertiary butyl group. Okay, so here this tertiary butyl peroxide is doing the work of this epoxidation as similar to this MCPBA. Now the stereoselectivity of the reaction is controlled by this diethyl tartarate, this tartaric acid, diethyl tartarate. If it is negative, then we will get another one kind of stereochemistry. If it is positive, we will get another kind of stereochemistry. This is called diethyl tartarate. You know that diethyl tartarate. You know about tartaric acid. This is tartaric acid. This is tartaric acid. Okay. So this is tartaric acid. Now diethyl tartarate means instead of this COH there will be two ethyl groups, CO2ET. Instead of this one there will be CO2ET. Okay. So if we use positive diethyl tartarate, we will get one kind of product. If we use negative diethyl tartarate, we will get another kind of product. So here the oxidizing reagent is tertiary butyl hydroperoxide, and the method relies on a catalyst formed from titanium tetride isopropoxide. So here titanium isopropoxide is acting as a catalyst which is controlling the stereochemistry, and diethyl tartarate. So this diethyl tartarate combines with this titanium isopropoxide and makes a stereochemistry which prefers the selective epoxidation. I am not going to the reagents here because it will be complicated for you. If you guys want to know more about this one, you can go and check Claydon in the asymmetric synthesis. There is a chapter, they have given this one. You can go and check from there. They have shown the active catalyst. You can go and check from there. I am not showing here, so I am just going to the problems and how we can approach to the questions and the tricks for those. Now the thing here, I have shown two examples. Suppose they have given this substrate, this allylic alcohol. Okay, the one point I have missed, for this type of epoxidation, sharp lip epoxidation, you can't perform sharp lip epoxidation on any alkene. That alkene should be an allylic alcohol. That alkene should be an allylic alcohol. This can perform sharpless epoxidation. But if you take just simple alkene, this is not can't be performed sharpless epoxidation. Okay, so this is one of the valid point, that for sharpless epoxidation your substrate should be an allylic alcohol. Without that, sharpless epoxidation is not possible. Now they have shown two examples. One is this one. Where they have added this titanium isopropoxide plus DMT. DMT is dimethyl tartarate. DMT is dimethyl tartarate. You have to use tartarate, any tartarate. It can be diethyl tartarate, it can be dimethyl tartarate, it can be diisopropyl tartarate. You have to use any tartarate. So they have used this positive dimethyl tartarate and tertiary butyl hydrogen peroxide. That's the short form TBHP, tertiary butyl hydrogen peroxide. This is the short form of this one. And in DCM at -20°C after 16 hours, they got this one as a product. Whereas in this case, when they use minus diisopropyl tartarate under same condition, they got this above one as a major product. Now how can we determine when this uh, we will get this below product and when we will get this above one. So there is a trick. Suppose if you draw the allylic alcohol in this way, how I am showing, where this allylic alcohol will be in the right side, right above. To draw this one as a this way, you have to draw this only, then this trick will work. Okay, if you keep this allylic alcohol at this place and perform this reaction, in that case if you have given plus diethyl tartarate or DMT or anything, diacetyl tartarate, you will give a wedge that is a positive, that is a above the plane epoxide. If you give negative, you will get a below product. Okay, so from that one you can, this is a trick. If you keep this allylic alcohol at the right side above, then whenever if you are given a positive diethyl tartrate or dimethyl tartrate anything, you will always get a above the plane product. If you are given a negative tartrate, you will always give a always get a below the plane product. Now suppose if you have the reverse one, if allylic alcohol is in this plane, in the left side, what will happen? Just reverse of this one. If you use positive, you will give this below the plane. If you use negative, you will get above the plane. It was a short trick for examination purpose, because sometimes we get confused with the positive and negative, that what will be the product, because the transition state of this one is not possible to draw in examination or anyhow in a pen or paper. It is bit difficult because it's 3D and it's a very big transition state. You can go and check in Claydon. I think everyone knows about Claydon. Is a book, Claydon. You can go and check from there the stereochemistry if you want to know the transition state of this one. It is it's quite difficult. So this is a trick. If you want to remember it like this way, you can go for that. Otherwise, if you have any other strategy to remind this one, that is also okay. So suppose this product has been given, okay, and they have given positive, this positive diisopropyl tartrate, and other conditions are same. They have given TBHP, that means this tertiary butyl peroxide, TBHP, this tertiary butyl hydrogen peroxide, and they have given this titanium isopropoxide. So what will be the product? So if we go through this tree, if we just turn it a bit and draw according to our easiest way. Then it will be like this. It will be like this. So as it is left hand side, and you are giving a positive, so what will be the product? The product will be below the plane. The product will be below the plane. So the epoxidation will be below the plane. Okay, now you can get it. The epoxidation will be below the plane. Now just answer what will be the stereochemistry of this one. In the similar way, if you just turn it, it will go left hand side, and as negative is given, so we will get a above the plane product. We will get a above the plane epoxide. Okay. Sorry, I had a issue with my network, so I got disconnected. So here you are. So I think everyone understood about that trick. So if that allylic epoxide group is left hand side, just after turning this way, if you just project this way, it will be, if we use a positive diethyl tartarate or dimethyl tartarate or diisopropyl tartarate, will get below the plane. If it is like this way, you will get the above the plane. So here, as after, if you just imagine it, after turning this allylic double bond, then this allylic alcohol will be in the left hand side. So as it is in the left hand side, so by using this positive, we will get a negative, the below the plane product, that is the below. Whereas if we, in the same case, if we use the negative diethyl tartarate, what we will get? You will get our epoxide which will be above the plane, that is a OH product. Okay. Now this is one of the question I gave in the last class as a homework to try by yourself, to go to the book and try to get the answer. So I hope you have tried. So let's try to get the answer. So they have the major product formed in the following reaction is. So what will be the major product formed in this following reaction? So this is an allylic alcohol. So this diethyl tartarate will always, titanium isopropoxide, tertiary butoxide will always form the epoxide of a allylic double bond. As I have mentioned, always the surplex epoxidation is selectively epoxidize the allylic double bond. So among these two double bond, which one is the allylic one? This one. This one is the allylic bond. So obviously these two options are already cut from our choice. Okay. So in this way, if you are attending the MCQs, just try to eliminate the option one by one first, then go into the whatever minor theories are there, just based on that just try to eliminate the options. Then you have to think of between only two options. There will be no more four options for your answer. So if you eliminate like this way, now the confusion is between these two. So now they have given a positive diethyl tartarate. They have given a positive diethyl tartarate. As we draw, as we see. So if you just see from this plane, this side, this allylic alcohol is left hand side. This allylic alcohol is left hand side. And if we have this allylic alcohol part in the left hand side, positive will give a below the plane product. So which one will be our major product? This one. It's very easy. If you know the trick, the answering the question is 10 seconds thing. Okay. So if you just imagine, see the allylic alcohol from this plane, then this allylic alcohol part is left hand side, so positive will give the below the plane product. So the correct option is option A. Let's go to the next one. What will be the major product formed in the following reaction? So they have given this product as isopropyl group, and they have given positive diethyl tartarate. Positive diethyl tartarate. Now just to understand according to our understanding, let's just, if you just turn it like this way, then what will be the stereochemistry? Here will be the isopropyl group and there will be the allylic alcohol. Now it is in the left hand side. It is in the left hand side. So if it is the left hand side, the positive will give a with below the plane product. So the positive will give a below the plane product. So this one. Now you can get confused between this and this. Which one? So always remember, during the epoxidation formation, before the epoxidation of this reaction, the stereochemistry of these two bonds are trans to each other. That is, they are in E double bond. They are in the opposite of each other. That is, their stereochemistry is trans to each other, or if you see anti to each other, or in a E stereochemistry. Now after the reaction also, the epoxidation is forming in a concerted manner, concerted step. This just oxygen is coming, this oxygen is coming from the above the plane or below the plane. So meanwhile this reaction is not stepwise. So meanwhile this stereochemistry of these two double bond will not change. The stereochemistry of these two double bond will not change. They will be if they are trans in the substrate, they will be trans in the product also. But here you can see in the product is trans, but here the product is cis. So the stereochemistry of these two groups has been changed. So this won't be our answer. So correct option will be option D. So during just attending the options, you have to be careful about everything. It's not about just if you see if you just get okay, it is down below the plane, you are just okay, this is our correct answer. You have to check the other stereochemistry of the other groups also. Now today's topic we'll discuss, that is reduction. We have discussed about the oxidations already, oxidation of carbonyl compounds, oxidation of alcohols, then oxidation of carbonyl and oxidation of double bonds. Now we'll discuss about the reduction. So there are large number of reduction methods are there. So I have tried to group them in this four manner. First one is lithium and sodium metal based reagents. Second is hydride donor. Third one is hydrogenation, and the other reagents are there. So first today we will discuss about the lithium and sodium metal based reagents. Lithium and sodium metal based reagent, and one of the important example of lithium and sodium metal based reagent is Birch reaction. important sodium and lithium metal based reagent is Birch reduction. So how this Birch reduction take place? So today we are mainly discussing about this Birch reduction because this is a small topic, but a lot number of questions comes from this topic. So I have tried to compile them as much as possible. There are other questions are also there based on this Birch reduction. I will try to compile them in the next classes. So what is Birch reduction? Birch reduction is an organic redox reaction that is used to convert an aromatic ring into a diene. So aromatic ring have a 6 pi electron, that means 3 pi electrons are moving there. So one of the pi bond will be reduced and we'll get a diene. So let's see how this goes. So reaction carried out by sodium or potassium metal dissolved in liquid ammonia in presence of alcohol. 2 hydrogen atoms are added at the opposite ends of the molecule at 1 and 4 position. This reaction can be applied in total synthesis of the natural products. So if we see the mechanism. So the mechanism is going through a radical pathway or one electron. This is single electron pathway where the single electron is being added into this aromatic ring. Now if we have electron donating group, the mechanism is bit different. If you have an electron withdrawing group, the mechanism is if you electron releasing group, it's electron donating or electron releasing group. Okay, it's both are same. So if you have an electron releasing group, the electron movement is like this way. So when you have an electron releasing group, this single electron at first comes to this ortho position, then the movement of electron goes like this way, and if it takes a proton, then it will be generation of negative charge, and it takes a proton from ammonia or additional alcohol. After that it will be like this structure, then another electron will be added to this center, it will be another negative charge, and it will take a proton, and you will get this as our product. Whereas in case of electron withdrawing group, the single electron first comes to the para position of the molecule, and through this mechanism it will give this as our product. So if you want to get a shortcut of this one, if you have a electron donating group, suppose this is, if you want to remember it in a short way, if you have electron donating group, just keep the double bond along adjacent to this one and draw a double bond opposite to that. So just if you have an electron donating double bond, the product will be like this. See, it's matching. Okay. Now if you have electron withdrawing double bond, electron withdrawing group in the ring, what will happen? Then just draw 2 double bond, keeping it in the middle. So this is a shortcut to remember for electron donating and electron withdrawing group. Now this batch reduction can be used for reduction of triple bond to a double bond, and in this case through batch reduction of the alkynes we will get a selective trans product in a major. From the, if you want to get a trans alkene from an alkyne, then you will go for batch reduction. So if you see the mechanism, the sodium will give one electron to this sp carbon, one electron to this sp carbon, and this double bond will move from here. After that it will form a negative charge, and this, due to this steric hindrance, this structure is less stable, so this undergoes a rotation and gets this trans, where this negative charge take a proton from there. After that, taking another electron at this place, it take a proton again, and will give this, get this trans alkene selectively. Okay, so now if you were given a alkyne and they have asked you to form a trans alkene selectively, you will go for which reaction? Batch reduction. Okay, so let's try to solve some questions based on this batch reduction. So they have asked the reagents required for the conversion of hex 3 ion to hex 3 in R. So they have hex 3 ion means there are 6 carbons. There are 6 carbons and the structure will be hex 3 ion, so 3 1 2 3 4 5 6. Okay, this is a hex 3 ion. Now they have formed this hex 3 ion. They have got E, they have got this trans or E alkene. Okay, so which reagent we will choose? So I have already discussed, from alkyne to alkene, to get a E selective product we will always go for batch reduction, and among these 4, which one is batch reduction reagent? This one. Okay, this is also an important reagent. This is called Lindlar catalyst. This is called Lindlar catalyst. Lindlar catalyst. So what happened with this catalyst is similar to this batch reduction, but in this case you will selectively get a cis product. You will selectively get a cis alkene. You will selectively get a cis alkene. Okay, so whenever they will ask you to form a cis alkene selectively or in a major portion, you will go for Lindlar catalyst. But if they ask for formation of a trans alkene or as E alkene, you will go for this batch reduction. Okay, let's solve the next one. So this is a simple one. The reaction is an example of, so they have given the example and asked which type of reaction is this: batch reduction, Wolff-Kishner reduction, Clemmensen hydride reduction. So now we know this is a batch reduction. Okay, which of the following reaction do not represent the major product of given batch reduction? So here they have given multiple substrates here and performed batch reduction and shown the product. Now they are asking which options are the correct. Which options are the correct? So among all these substrate, which one will give after batch reduction, which will give this as the major product? So if you see this one, this is a xylene, there are two methyl group in the para position, and alkyl group, due to its plus R effect, a plus I effect, it considered as a electron donating group or electron releasing group. So whenever there is electron releasing group, what is the trick? Just keep the double bond adjacent to this. So this can be formed. So this is the correct product. This is the correct option. Next is the benzene. Benzene, there is no such group is there. So this can also be formed. Third one is this one. Here methyl group is there. Methyl group has also plus I effect. So we have to keep this double bond intact. So here they have kept this double bond. So this can also be possible. Now this is the acid group. Acid group is the electron withdrawing group, and whenever there is electron withdrawing group, what is the trick? You have to keep this between, and there will be two double bond opposite to that. So this is not possible. So this option is not correct. Same this naphthalene. This is also possible. This can be also possible, as this is benzene ring. Just you have to just reduce it. Next is this phenanthine ring. Sorry, anthracene ring. In this ring, anthracene ring, in the anthracene ring, whenever we are doing this Birch reduction, we have seen to get reduced this middle it formed this. For anthracene, we have found to get this product, because if we reduce, so that because the middle ring is more electron deficient. This middle ring is more electron deficient. That's why when this electron added, this added to this middle ring. Okay, because this middle ring is the more electron deficient. So this will be the product. So this is not correct. This is not correct. Now they have taken 2-butene, they have taken butene and perform this. So in this case you will get a transalkene, obviously. So this is also not correct. Some options problem is, so all this there is some options problem is there. So all this will be the correct option. Okay, let's go to the next one. This one I have gave one of the homework in the last class. So now yesterday in the last class I have talked that we will know about this concept in the next class, then we will be able to solve this one. So just for a curiosity, so that you can try to get the answer. So now you know that Birch reduction, and this is a electron donating group, electron donating electron. So all the three are electron donating group. Whenever you are if you have such kind of substrate where all the groups are electron donating, you have to consider which one is more electron donating. So this one is more electron donating because of this plus R effect, because of its plus R effect. So we have to consider according with respect to this. So if you consider with respect to this, the double bond will be there. One double bond will be here. There is a methyl group. There is a OMe group. there is a ethyl group. Okay, this will form after Barch reduction. This will form after Barch reduction. This will form after this Barch reduction. Now they have added ozone and methanol Me2S. Ozone they have added, so that means ozonolysis will form, and they have also added Me2S. That means there will be no further oxidation. So reaction will stop at the aldehyde step. So you have to cleave the double bonds. You have to cleave the double bonds. Now among these two, which one is more electron donating double bond? This one or this one? Obviously this one. So this double bond will get cleaved, because whenever ozonolysis this goes for the electron rich double bond. I have talked about this in the last class. Ozonolysis always favors the electron rich double bond. Electron rich double bond. So this double bond will be cleaved. There will be an ethyl group here. So which one is our product? There is the ethyl group. Stereochemistry of this trans. So this methyl and it should be trans. So option C. Okay, just you don't get confused between these two. You have to see this methyl and this CO2Me is in trans. After if just epoxidation before, this group and this group were trans to each other. So the stereochemistry will not change. The stereochemistry will not change. So they are trans here. So it should be trans always. So the product will be option C. Okay, let's go to the next one. Reaction of metamethyl anisole with lithium in liquid ammonia and tertiary butyl alcohol at -33 degree generates the compound X as the major product. Treatment of the compound X with dilute sulfuric acid produces the compound Y as the major product, and the compound X and Y respectively are. So they have taken, just go whatever they said, they have taken metamethyl anisole. Anisole, you know, this is called anisole. OCH3 group attached to a benzene ring, this is called anisole. So they have taken a metamethyl anisole. So there is a meta position, there is a methyl. So they have performed liquid ammonia and tertiary butyl alcohol in lithium salt. That means lithium NH3 and tertiary butyl alcohol. So what will form? It will form a Barch reduction. Which double bond will be reduced? Because this is the more electron donating group, so we have to consider this one and draw the product. So after the reduction, this will be our product. Okay. Now the treatment of this X with dilute sulfuric acid produce the compound Y. So X is this one. So just get the X. So the option will be between A and B are already cut, because option will be this X is in these two options, option C and D. Both are already cut. Now next they have added dilute sulfuric acid. So sulfuric acid I am just drawing as a H plus. Dilute sulfuric acid, that means they are giving the H plus just. Now what will happen in presence of H plus? If you see, this is a ether. This is kind of a ether. This is kind of a ether. So in presence of H plus, these get hydrolyzed and form this as our product. Now you can see this is a enolic OH. This is a enolic OH. Now it goes through a ketoenol tautomerism. Ketoenol tautomerism. Undergoes a ketoenol tautomerism, and this comes here. So what will be the product? And form this as our product. Now to get a conjugation stability, this double bond, sorry, now get a conjugation stability. There is a proton, this double bond will be, there will be double bond shifting, this goes here and this comes here. So the correct option will be option B, sorry, C. The correct option will be option C. Okay, understood? The last step is just hydrogen transfer, just to get a conjugation stability, just to get a conjugated double bond and conjugation stability. This hydrogen comes here, and so that the product get a conjugation stability. Okay, let's go to the next question. The compound formed in the following reaction sequence. So they have given this one, and what will be the first one is the Birch reduction. You can see that in every year in NET and GATE there is one question formed. Birch reduction is almost there, so it's one of the important topic. So they have given this one, what will be the after first step, as it is the electron donating group. This is the electron donating group. This is the electron donating group. So we have to, according to the what trick, I am not going again and again. So the product will be this one. So now if you just add H2SO4, this will get hydrolyzed, and similarly it will undergo a tautomerism from this. Now to get a conjugation stability, this H transforms from here, and this goes here, and you get this as our product. Okay, that's simple. Let's go to the next question. What will be the major product of the following reaction? So from the reagents you can see this is a Barch reduction, this is a Barch reduction. So obviously it will give a trans product. So the correct option is option C. So the correct option is option C. Let's go to next one. The major product X and Y formed in the following reaction sequence are. So what will be the major product formed X and Y? So as it is from the reagents lithium and liquid ammonia, whenever you see lithium and liquid ammonia or sodium or liquid ammonia, you will just think about Barch reduction. You will just think about Barch reduction. So it will be a Barch reduction. Both are electron donating. This one is more electron donating. So which one will be our top? These two are not possible because 1,4 diene will be there. So correct option will be between these two. Now they have added O3, that means ozonlysis will be performed. Now between these two double bond, which one? Both are same. So which double bond is more electron donating? This one. So you will just cleave this double bond. If you just cleave this double bond, which one form? This one. So the correct option is option D. Correct option is option D. This has formed by this has been formed by cleaving this double bond, and this has been formed by cleaving this double bond. So the among these two double bond, which one is more electron donating? This one. So the correct option will be option D. Okay. Let's go to the next one. The major product P of the given reaction. What will be the major product? So they have given liquid ammonia, tertiary butoxide. Now I have seen this Barch reduction we have used for aromatic ring reduction. We have used it for alkyne reduction. Now this type of Barch reduction can be applied for double bond reduction also. But in that case the double bond should be an electron deficient double bond. The double bond should be an electron deficient double bond. So by using Barch reduction, we have already learned about the aromatic ring reduction. Aromatic ring reduction. We have known about the alkyne reduction. Now this can be also used for alkene reduction, but there is a specificity that the alkene should be an electron deficient double bond. And how that can be possible? If any electron withdrawing group is connected to the that alkene will be electron deficient double bond. So just like H2O2, you know about that electron deficient double bond can be epoxidized by using H2O2. In that way, how we can determine that the double. Hello.
Hello. Can you repeat it? I did not hear the question.
Okay. So we have in the last 2-3 slides we have talked about that Barch reduction can be used for aromatic ring reduction. So aromatic ring can be reduced by this Barch reduction. Then we have shown some example also. After that, this Barch reduction can be used for alkyne reduction. If we take a alkyne, then Barch reduction will specifically give a trans product that we have talked. Now the thing is, Barch reduction can be used for alkene reduction also. Barch reduction can be used for alkene reduction also. That if you want to make a alkane from a alkene, that Barch reduction can be applied for that case also. If you want to make a alkene to alkane, that can be done from a Barch reduction also. But the requirement is that double bond should be an electron deficient double bond. Means there should be any group connected to the double bond which withdraws the electron from the double bond. We know any double bond or triple bond are quite electron rich because of the pi electron cloud. So there should be any electron withdrawing group connected to that, which will attracts the electron density from itself, and the double bond becomes a electron deficient double bond. So this type of alpha beta unsaturated double bond, you know, this type of double bonds are electron deficient double bond. Why? Because of this carbonyl group there is a conjugation where this double bond can go through this resonance, it goes here, and there is a positive charge can be generated. So because of this electron withdrawing effect of this carbonyl group, this double bond becomes a electron withdrawing, electron deficient double bond, and this type of double bond can be reduced by using Birch reduction, and this double bond will be just reduced and we will get this as a product. Thus double bond will be get reduced, nothing else. The mechanism is quite similar. If you go into the mechanism, this lithium will give a electron at this place, this moves here and it forms one electron. There will be one electron here. In the next step, it will take a proton from this alcohol. It will take a proton from this alcohol and form this one electron here. After that, again another molecule of electron will be donated.
Ma'am, you mean? Excuse me, ma'am.
Sorry, what?
Excuse me, ma'am.
Yes.
Ma'am, is that a negative charge on the tertiary methyl group next to the carbonyl group? Like that's a tertiary carbon, right?
This tertiary,
ma'am,
this is just a alcohol.
After transferring,
this is just a alcohol. I have just shown this is negative charge.
No, the second after. Yeah. So, ma'am, that is on a tertiary carbon, but it's stable, right?
There is no such.
But that's not.
This is a
stable.
This is the intermediate. It's
okay,
not like it's not. You are not getting it in a hand, because just like when you are attacking any, like we are showing some. If you are attacking any alpha beta unsaturated double bond, we are showing this like there is a formation of negative charge here. We are not getting this in hand. This will be obviously this is very unstable, so that's why it will take a proton from this place and it will get protonated to give this one. It is very unstable. That's why reactivity is too high. Then again another electron will be given by this lithium to at this place, and it will form again a negative charge, just like Birch reduction mechanism, simple mechanism. It will form this negative charge here, and it will take again another proton and we'll get our product, this one. Okay, so let's go to the next one. So today in the first session of these classes we discuss about surplus epoxidation, that if we have an allylic double bond, how surplus epoxidation, by using surplus epoxidation we can form a epoxidation in a stereoselective manner. Just by changing the nature of the reagent we can form a above the plane epoxide or a below the plane epoxide. Now first step, they have added this lithium aluminum hydride NaOH and got a and after surplus epoxidation they will give we have to determine what is A and B. Now this lithium aluminum hydride can also reduce a triple bond, but that is also as it is going through a lithium salt and I haven't discussed about this lithium aluminum hydride yet. When we will discuss about this one, I will show the mechanism in a perfect way. Just for now, just remember, whenever this lithium aluminum hydride is given to any triple bond, it will always give a trans alkene. It will always give a trans, that it will be a trans hydrogenation. So among these four, these two are already cut because of C's. So these two will be there trans. So whenever this lithium aluminum hydride is added to any alkyne, this alkyne will be reduced to trans alkene, just similar to Birch reduction. The mechanism I will discuss when I will discuss about lithium aluminum. I will discuss there. Now they have given this surplus epoxidation reagent. They have given surplus epoxidation reagent. Now in this, while we are discussing about the surplus epoxidation, what was the main criteria of surplus epoxidation? The double bond should be a allylic double bond. Any double bond can't be epoxidized by using this surplus epoxidation. Only the allylic alcohol double bond, which is the allylic alcohol double bond, that can be only epoxidized by using this surplus epoxidation. If you want to know about why this allylic alcohol is requirement, if you have to see the stereochemistry of the transition state, where the OH group is holding the total reagent part and just controlling the stereochemistry of the reagent. So if the stereochemistry is bit in 3D, if you want to know, you can go Claydon and check. There is a asymmetric synthesis, there is a chapter, you can go and check from there. I have in a 2D, it's bit difficult to draw here. You can go and check there, because OH is important to control the stereochemistry of the reagent. That's why allylic the surplus epoxidation can be only performed for allylic alcohol. So only this double bond will react, only this double bond will react. So in this case both the double bond reacted, in this case only this one has been. So from there you can just by seeing this you can correct the option, you can just tick the option, okay, this one will be the correct. Now just for simplicity, just for a clarity, I will just give a review of the overview of this. I have already told, if you see from this plane, from the here, if this allylic alcohol, if you see from here, okay, and allylic alcohol is in the right hand side, and you are using a positive diethyl tartrate, what you will get? You will always get a above the plane product. See, you are getting a above the plane product. Okay, the trick I have discussed already in the initially in the class of this class. You can go and check from there again if you have forgotten it. So whenever this allylic alcohol is in the right hand side, you will just go, and you are using a positive diethyl tartrate, you will go for the above product. This is a trick to remember this one. So correct option is option C. Now next is the major product A and B in the following reaction sequence. You have to determine what is the major product form in A and B. So this is a Birch reduction again. So you can see in almost once in a while, in every year you are getting this, like alternative year also we are getting this one question from Birch reduction, simply from Birch reduction, or they are combining Birch reduction with another reaction, but they are including Birch reduction a bit. So if you add this Birch reduction, this is the electron with donating group, so it will control the stereochemistry of this double bond. So I have shown the trick. If whenever there is an electron donating group, just draw the group, and there will be adjacent double bond will be intact, and there will be a double bond just opposite to that. So this will be the structure. Okay, now they have added MCPBA. Now we know that MCPBA epoxidizes the double bond which is electron rich. Whenever MCPBA is added, MCPBA choose the double bond which is more electron rich. And if you are adding hydrogen peroxide, that is H2A2, that will choose electron deficient double bond for epoxidation. And MCPBA will choose a electron rich double bond.
Excuse me, ma'am.
Yes?
Excuse me, ma'am.
Yes.
Ma'am, won't option C or B can be A, ma'am?
sorry, option C or B means what are you saying?
Ma'am, it's like the option. Can it be A, ma'am? Because there also methyl is also like plus I effect, no, ma'am. So like yesterday what sir has said, like he told option A would be. We discussed a similar question. So he told option A would be there, the answer.
Option
From I think that's what he said. I don't remember
option
exactly.
option A will be the correct
A,
answer.
like no, sorry, the option B. No, no, not option A. Option structure A in option B.
Okay, okay. If you draw this, okay, it is. If you draw this way, there will be just conjugate. Only this double bond is in conjugate. But if you draw, okay, I have missed this one. If you draw this in a, if you just this way, then both the double bond is in adjacent to these two electron donating group. Yes, thank you for correcting me.
Yeah.
I just missed it. In this case, if you draw in this way, what is this? The double bond is only connected to only one electron donating group. But if you draw in this way, both the double bonds are connected to the electron donating group. So this is favorable in this case. Thank you. So after the epoxidation, which will the epoxidation will form? Obviously, the electron needs double bond. Then this double bond will be form epoxidation. So the correct option will be option B. So the correct option will be option B. So this is one question. So this is the last one. For just we have discussed a lot about this batch reduction. I think you can try this one by yours. So I am just giving it as a homework. If we will discuss in the next class. So you can try by yourself what will be the product for this reaction, and we will discuss in the next class. Next class we will discuss more questions. If I will try to collect more questions on this batch reduction, and we will discuss about the reagents, hydride type reagents like the LiLH4, NaBH4 and all. We will discuss about those in the next class. Okay. Thank you. Have a nice day.
Okay, ma'am. Thank you.
Thank you.
You too, ma'am. Thank you.